Hello everyone, my name is Naje George and I will be discussing with you mimetic methods for ab-initio quantum dynamics. Specifically, in ab-initio quantum dynamics, I'm going to be discussing non-adiabatic molecular dynamics, otherwise known as NAMMD. So NAMMD is characterized by requiring explicit time integration of the Schrodinger equation for nuclei and electrons. However, methods such as Tolle's fewest switches surface hopping can be used to reduce the computational cost of NAMMD simulations because this does not require the explicit time integration of the Schrodinger equation for nuclei. Instead, we derive that at a certain nuclear position, we get a Schrodinger equation for electrons that we then integrate. Specifically, in this work, we're going to be focusing on deriving a unitary propagator that preserves the symmetries of an interacting chemical system. As stated before, for each nuclear position R, which is determined based off of classical Newton dynamics, we derive a time-dependent electronic Schrodinger equation as the following, in which the Hamiltonian is the attraction and repulsion of electrons and nuclei, as well as a time-dependent potential. We determined that this electronic wave function can be expanded in the Born-Oppenheimer basis as follows, which is a sum of vectors and Born-Oppenheimer states. Inserting this expansion into the electronic Schrodinger equation provides us with this matrix discretization, which is basically a propagation of an amplitude vector we define as C, which comprises of in which the propagation comprises of the following parameters below. So here we can describe the formal solution as an amplitude vector at some time being equal to a propagator being applied to an amplitude vector at an initial time. We describe this propagator as the time-ordered exponential of I times an integral of our Hamiltonian. And this integral of the Hamiltonian is interesting since the Hamiltonian is time-dependent, which means that we cannot compute this integral exactly. So we describe that the unitary propagator has this property where the derivative, or the partial derivative of it with respect to time is equal to the Hamiltonian being applied to said unitary propagator. And with that, we can describe our unitary propagator as a matrix exponential which can be approximated with a Magnus expansion. This Magnus expansion will account for the time ordering of our exponential, and it will enforce time reversal symmetry. In addition, we're going to be using a 2-point Gaussian quadrature to construct a fourth order Magnus expansion to fully approximate our unitary propagator. So I wanted to look at previous work that was done using mimetic methods on a time-dependent Schrodinger equation. So here we have a simplified discretization of a Schrodinger equation with a time-independent potential. And using second-order mimetic operators and a center time, center space scheme, we observed that there was a second-order rate of convergence within our errors. Now, this previous work is important because there are some key insights that I gained when doing this research. One is that the CTCS scheme was chosen due to it enforcing that time reversal symmetry that's necessary, very similar to an implicit scheme. With this time reversal symmetry, I observed that there is a conservation of norms in the propagation. However, at smaller time steps, which had influence on, at smaller spatial steps, which had influence on the time step, the rate of convergence dropped, and this was particularly noticeable around the boundaries, that the boundaries weren't being approximated correctly. I predict that this was due to the propagation not being entirely unitary at these smaller step sizes, and I do also predict that using these Magnus expansions will result in a more accurate propagation because of the fact that it'll preserve the unitarity of the propagator. As far as future directions go, as I mentioned before, I'm using a 2-point Gaussian quadrature. There's investigation being done to instead implement a Gauss-Chebyshev quadrature, which should result in less propagation errors. There's also investigation into the computational costs of constructing multiple powers of Hamiltonians, And this will be done to determine the value of performing higher order Magnus expansions to more accurately capture our unitary propagator. And then finally, all the knowledge that has been learned throughout this research will be implemented into a mimetic methods algorithm for testing. Thank you. I hope to see you at my poster.